Kuldeep sir, Dr. Kuldeep, are you? Yeah, please.
Yeah, sir. Good morning.
Good morning. I'm going to make you presenter 1 minute. Yeah.
Please make the presenter to
Yeah.
Kuldeep. No, sir. Not Dr.
Okay.
Kuldeep. Kuldeep only.
Okay. Yes, I think so.
Yeah. Now I can see.
It's working. So I think, sir, we should start it.
Fine, sir. Fine. Yeah.
So good morning, all the participants. Once again, this is session 2, day 4 of this FDP, and it was clear that what we are going to cover in this session. It was announced by the Dr. Kuldeep yesterday also, and today morning session also I clear it. He is going to continue his session from where it was left out yesterday, and will be going to be little bit hands-on that session, and hope you will enjoy it. So Dr. Kuldeep, please continue.
Yeah, thank you, sir. Thank you so much. I hope I'm audible and I'm visible, though visibility is not needed, but yes. So is it fine to everyone? Very good morning, everyone. Yeah, Dr. Chinmay audible. Others? Yeah, thank you. And my screen is also visible, I believe, right? I have shared the screen, I think. Is it? Yeah. So, very good morning, everyone. Again, we are here for this SVD, wonderful topic, SVD. And as I said yesterday, that we'll be doing some hands-on that you are more interested in. And I mean, yes. So any particular query, anything from your side? The screen is not visible. I think, ma'am, it is visible because I have logged in from 2 devices and I can see that, yes, it is visible. So is it visible to others? Yeah, visible. I hope so. So then now visible. Okay, fine. So I hope you all can see this screen. Okay. So any particular doubt? I'll start from the queries. I'll start from the concerns. If you have any from the previous, I mean, yesterday's talk. Anyone? Anyone from the audience? I hope some of you are from, I mean, yesterday also, I know I can recall the names. So Vishal was there, I think. Yeah. So anyone having any concerns? Okay, no problem. So what we will be doing, I completed the theoretical part of this SVD, right? But I mean, no hands-on, nothing, no example was done, right? So someone was asking also that, yes, some hands-on to be there. So I'll very quickly recap all those things which I did, because those will be required in our today's session. So what we started with the singular value. The singular value is nothing but related to eigenvalue, but it is the square root of eigenvalues of AA transpose. So we wrote this algorithm that if we have A, we can find out A transpose, then we can find out AA transpose, then we can find out its eigenvalues, take the square root of that, and those will be called as singular values of A. Right. So till here it was okay. The beauty about this concept is that it can be used for any matrix. So I give this example: if you have a matrix of 5 cross 3, eigenvalues we cannot find, but yes, singular value we can find, right? So I mean, we are hopeful that yes, our data matrix is always not squared, so we can apply this concept because it is applicable to any matrix. Eigenvalue decomposition, the idea behind eigenvalue decomposition, that yes, it is a very old concept, and eigenvalue, I discussed about a little bit about eigenvalues, right? So eigenvalue, yeah, this is about eigenvalues. I discussed that, okay, what actually eigenvalue means, and why do you think that this is the wonderful concept, this is the wonderful thing to study about. So then I discussed about eigenvalue decomposition, and you saw there are two problems in this eigenvalue decomposition. What are the problems? First, if the matrix is not a square, you are finished. And it might happen that U is not invertible. That matrix U, whatever you are doing in eigenvalue decomposition, U lambda U inverse, So U may not be invertible. Then how will you find the U inverse? I mean, then again you are finished. So, but we are hopeful that yes, we'll do something better, right? Then we took that yes, if the matrix AM is symmetric and positive definite, then this at least this problem of inverse is gone. We don't need any inverse. Then U can be decomposed as U lambda U transpose. Happy, but is still that problem is still there. What the problem is? Being the matrix is square. That problem is still there. We don't want that. Then we went to that. Yes, our claim is, this is what I discussed about Cholesky factorization. So Cholesky factorization is applicable for the symmetric and positive definite matrices. So I discussed a little bit about Cholesky factorization. If you are not interested, you just leave it, right? And then for any general matrix of order m cross n, not necessarily square. And the answer is yes. And the method is singular value decomposition, right? So what is the singular value decomposition? USV transpose. That any matrix A can be written as A U S V transpose, where U is something, S is something, V is something. What is that? U, S and V. So I wrote the dimension also. If you see A, if A is your M cross N matrix, then U will be M cross M, S will be M cross N, and then V transpose will be N cross N, and immediately you can find M cross N. So what is that? S, singular values of A. But please note that what would be the singular values of A? Those will be nothing but square root of eigen values of AA transpose, right? So S will be this. Then U will be eigen vector of AA transpose. Here it is. ये iPad से इसमें करने में थोड़ा सा कट जाता है कभी-कभी, but it's okay, right? So this is eigen vectors of A transpose, and V is the eigen vectors of A transpose A. I have, then this is what the claim, right? That A can be decomposed in U S V transpose. Then U is this, S is this, and V is this. But did I prove that? No, I did not give you the proof that why, how this has happened. Then only a few of you were interested in this, and I gave you a mathematical proof that you can also leave if you are not interested. Since this FDP is an advanced version of that, so I thought of sharing with you, because these things in a one place you may not obtain, right? At several, you have to go at several places to see all those things. So inside of FDP, this SVD is actually, I mean, how this has happened, how this equation 3 star you obtained. This is the key point, right? So how this equation 3 star you obtain, that insight I gave about this, that yes, you have two vectors, orthonormal vectors in row space, and this is easy to obtain, no problem for a mathematician. For a computer scientist, I would say that they can assume it. And you two vectors you have in column space, then you can write what actually you are doing. You are applying that A, matrix A on V. See, in your data also, you see what you have some data, you apply something on that, and you get some new thing, and that you say that yes, this new thing is of my use, this new thing is efficient, accurate, and it is of my use. So this is what I discussed, that okay, that's how this AU equals to sigma V, and I proved, I mean we proved, if you see here AA transpose, you see that V is nothing but the eigenvector of A transpose A. Right? V is the eigenvector of A transpose A, and this is the eigenvalues of A transpose A. So if the sigma square, sigma 2 square, sigma r square as the eigenvalues of A transpose A, what do you think? What would be the singular value? It's square root, right? So sigma 1, sigma 2, sigma r will be the singular value of A. Everyone convinced till here that V is the, this we proved, right? And similarly we proved for A, U, that transpose A are same. So if eigenvalues are this sigma 1, sigma 2, sigma r, then singular value will be what? Sigma 1, sigma 2, sigma r. So this is what the procedure I wrote, that yes, if you have A and you have to divide it into SVD, right? So what you need to do, you first find A transpose, you first then find eigenvectors of, this is eigen this is typo, right? Eigenvalues of A transpose, then eigenvectors of A transpose, that would be your U. Find A transpose A, find eigenvalues of A transpose A, that is same, and eigenvector of A transpose A is nothing but your V. What would be your S? That is nothing but a square root of eigenvalues of A transpose. So what was the eigenvalue? Sigma square, sigma 2 square, sigma r square. So its square root is nothing but sigma 1 square, sigma 2 square, sigma r. Now we have U, S, V for any general M crossing. So till here is fine to everyone. I mean, I just recalled whatever we did. So anyone please do message so that at least I can understand whatever I'm saying, it is reaching to you. So anyone, yeah. Thank you, Abhishek. Dr. Manisha, thank you. Dr. Ganesh, thank you so much. So any concerns to any one of you, anything you feel that yes, something is missing here? So today, as I said, that I'll start from hands-on, but before that, I just want to confirm that any concern, I mean, any query in this, whatever we have done, of course, we did all mathematical. The reason was that you should understand what is happening behind this SVD. Anyone? Okay, so now the time for example, right? So MATLAB is shared. I think you can see because I can see. So right. So first thing, very first thing, what we should do? We should do one example, right? So I'll define one matrix A. Right, simple. A is there, 4, 3, 8, 6. Anyone knowing the command for SVD in MATLAB? Anyone? Command for SVD in MATLAB? How the syntax actually? Some of you must be aware about MATLAB. I mean, I know you people are very comfortable in other languages, but anyone? Seetal, no. Okay, anyone else? No. Okay, fine. So I'll do, right. No issue. So this is the command for SVD of A. USV equals to SVD of A. You see, you are getting 3 matrices U, S, and V. Can you tell what is S here? Anyone? What is S? What I told. I mean, see what we did in theoretically, what I showed, I'll just justify today that yes, singular value matrix. Good, Abhishek. Yeah, thank you, Abhishek sir and Shashi Bhushan sir. Yes, singular values. So what was those singular values in terms of eigenvalues? In terms of eigenvalues, this was the square root of eigenvalue of A transpose A. Is it? Am I speaking correctly? Square root of eigenvalues of A transpose A. This is what I mentioned, right? Theoretically. Yeah. Ganesh sir, yes, right? So what are the S values here? And S is the singular value having on the diagonal. So one is 11 and one is 0. All of you agree with me? One is 11, one is 0. Agree? So then we just compute the eigenvalue of A transpose A and its square root. Please note that. Wow, yeah. That means whatever we proved mathematically, that was correct. Everyone can relate it at least. See, should I zoom it? I mean, is it clearly visible? Please do let me know. See, please do let me know that. I mean, it should be very crystal clear. Yeah, online nahi hona chahiye, yeah, offline hona chahiye. That's why I do it in a very slow pace. So he said that yes, eigenvalue command is this, A transpose A is this. I should zoom it if I can. Yeah, I think it is now zoomed a little bit. Is it? I think more clear. Yeah, it is more clear. Right? Rajeshwari, thank you. Ganesh sir, thank you so much. So you said that yes, लेकिन zoom करने में फिर वो problem आ रही है because we cannot see all these things. Okay, so S is this and eigenvalues are same, right? So square root of eigenvalues of A transpose A is nothing but what is the entry of S. So that means whatever we proved mathematically, that is correct. But one pattern you can see here. What is the pattern you can see? So I should mention that your S matrix will always have the singular value in decreasing order. तो पहले वाले पे जो एंट्री होगी ना वो सबसे बड़ी होगी, because here it is what, this is sigma 1, right? ये क्यों इतना ऐसे गड़बड़ कर रहा है पता नहीं. ये this is sigma 1, this is sigma 1, right? This is sigma 2, this is sigma 1, this is sigma 2. सो सिग्मा 1 हमेशा बड़ी होगी सिग्मा 2 से. सपोज अगर एक सिग्मा 3 भी होती, राइट? सो एस विल बी अरेंज्ड इन सच अ वे कि जो पहली डायगोनल वाली S will have the singular values in decreasing order. First of all, that much you understood, that S will have the singular values in decreasing order. देखो यहाँ वो दे रहा है इस ऑर्डर में आइगन वैल्यूज, पहले ये दे रहा है, दूसरी ये दे रहा है. All of you, please do understand that first eigenvalue he is giving this square root of eigenvalue, second square root of eigenvalue is giving this. But in S, if you see, it is arranged in reverse order. So I'm explaining that why it is so, that S will always have these entries in decreasing order. पहले diagonal पे सबसे बड़ी, फिर उससे छोटी, फिर उससे छोटी, फिर उससे छोटी. So is it clear to everyone? Please respond. Anyone having any doubt, any query? Vishal, thank you. Others, Jeetal, yeah. So it is clear, right? So S is fine. So singular value, we are very comfortable. We have any Dr. Manisha, thank you. Everyone, Dr. Shangita. So thank you, everyone. So S is the singular value of A, that is nothing but square root of eigenvalues of A transpose A. But please note that, and this is important, Roshni, thank you, Roshni. So important thing is that entries of S are arranged in decreasing order. सबसे पहले सबसे बड़ी, उससे छोटी, and it has a very strong significance. Also just now. So it has a very strong significance. But before that, I just want to show one more thing. What I showed you, कि ठीक है, S is the singular value. So we are happy. Whatever we proved mathematically, it is done. Agree. But we proved one more thing now. What we proved? That yes, U is the eigenvector of AA transpose. Right? And V is the eigenvector of A transpose A. This is what we proved mathematically. And it should come there. Isn't it? So A transpose A का जो eigenvector होगा वो V होगा. देखते हैं कैसे? You see, eigenvector of A transpose A, right? You see, there is something P, there is something Q. So Q is nothing but the eigenvalues of A. तो अगर आप 11 क्या था, ये स्क्वायर रूट था, ध्यान रखना. तो A की जो A ट्रांसपोज A की आइगन वैल्यूज जो है वो क्या है, 125 है. 125 का स्क्वायर रूट लोगे तो 11 ही आएगा. So this command gives you P is the eigenvector, Q is the eigenvalue. तो eigenvalue तो अभी हमें टेंशन नहीं लेनी, because we have already discussed that S is correct. Whatever we have proved, this is correct. But what about P? And P, और यहाँ पे मुझे टाइप करने दो V. Wow, isn't it? Whatever the claim, it was correct. Yes, P was the eigenvectors of A transpose A, and you can see here P is giving you the eigenvectors of A transpose A, and V was what? Eigenvectors of A. I mean, V was what? We got after SVD, and we see that yes, both are same. So whatever we proved mathematically, this is correct. This is showing, I just showed you in the MATLAB that yes, what? That if you calculate the eigenvectors of A transpose A, right, P is the eigenvector, Q is the eigenvalue. So eigenvalue too, I just leave it, right? So P is the eigenvector of A transpose A, and you have already seen that V is the singular vector, right singular vector. So what we call it, V as a right singular vector. क्योंकि आप देखो, आप कैसे लिखते हो A को? This is called right singular vector. V is called right singular vector. U is called left singular vector, right? So हमने यहाँ proof किया था कि V is nothing but eigenvector of A transpose A and we verified here. Yes. देखो ना V में जो आपको एंट्री मिल रही है, पहला कॉलम दूसरा कॉलम चेंज हो सकता है, डजंट मैटर, राइट। यहाँ पे क्या है, पहला आइगन वेक्टर ये है, तो यहाँ पे इसने दूसरा लिख दिया, उससे कोई फर्क नहीं, ऑर्डर डजंट मैटर, राइट। और वो उल्टा क्यों आ रहा है, दैट कैन एनीवन ऑब्जर्व व्हाई इट इज कमिंग रिवर्स? See, can anyone observe that why it is coming reverse? That P में पहला कॉलम आ रहा है 6 and 0.8 और यहाँ पे दूसरा कॉलम आ रहा है 0.8 0.6, जबकि V में उल्टा आ रहा है। Can anyone observe that? See, these are the small things which you should. Yeah, Ganesh sir, can you tell the reason why it is coming? Okay, ठीक है, no problem. So the idea is that it is taking the eigenvalues in the reverse way ना, पहले ये 0 ले रहा है फिर 125 ले रहा है, और SVD क्या करता है, फर्स्ट लार्जेस्ट आइगन वैल्यू लेता है और फिर वो छोटी वाली आइगन वैल्यू लेता है, राइट। सो मोनिका, या all of you got the point, right? That's why it is coming in reverse way. But those who knows the theory of eigenvalue and eigenvector, they know that order doesn't matter, right? So first vector is there, second vector. In the similar way, you can see that yes, अगर आप U निकालना चाहें तो U क्या होगा, A transpose, A transpose ये आया, and here you type U. You can see that eigenvector for AA transpose is nothing but same as P, which you obtained from eigenvector of AA transpose. जो U था हमारा, agree? देखो माइनस प्लस से फर्क नहीं पड़ता, बिकॉज दोनों माइनस है, तो माइनस यू कैन टेक कॉमन, राइट। इन eigenvectors, those who knows the theory of eigenvectors, they don't bother about it. वो दोनों माइनस है, कॉमन हो सकते हैं, ठीक है। और तो यहाँ पे भी देख रहे हो ऑर्डर रिवर्स है, दैट reason I told, because it is every time taking smallest to largest, but SVD take largest to smallest. But P and U are same. That means yes, in SVD, what is U? U is nothing but the eigenvector of AA transpose. V is nothing but the eigenvector of A transpose A. Right. S is nothing but the square root of eigenvalues of A transpose A or A transpose, क्योंकि eigenvalue दोनों की same. Wow, we are happy. I mean, any matrix, MATLAB क्या कर रहा है? I know what MATLAB is doing. MATLAB, we give any matrix A, what MATLAB is doing? MATLAB is computing whatever the procedure I wrote. This is what MATLAB is doing. क्या कर रहा है वो? Find A transpose, then find its eigenvalues, then find the eigenvector, that is U. Find A transpose A, find eigenvalues, then find the eigenvector, that is V. And A को up, and S already he knows that is square root of eigenvalues of A transpose, and that's it. He is giving you U, S, and V. So with example, this SVD is clear. Any concerns? Now I'm ready to take. Anyone? Or is it clear that yes, what theory says and what it is doing in MATLAB, we have verified it and we have understood it completely. Anyone? And I mean, anyone from the audience, if you say something, I'd be, I mean, it's good. Anyone? I mean, everyone got this idea, because after this, I'm going to do this PCA and other things. But before that, I just want to mention this one example, because see, one way is that I should have computed this eigenvector eigenvalue manually, but yes, MATLAB is also doing the same. So idea behind this SVD, everyone, अरे कोई तो बोल दो at least. तो as I told that your comments are the lifeline for a teacher in online mode, right? So thank you. Otherwise, I mean, it's very difficult whether you are getting or not getting, I don't know. I mean, right? Anyone having any concerns? I have done using Python. It's working. Thank you. Thank you. So it's working. But more than working, Dr. Manisha, I would say the logic is you should understand that yes, why this is, I mean, why I told this. I just wanted to explain the theory of this mathematical approach, eigenvalue and eigenvectors, which gives us the beautiful concept, this SVD, right? Okay, no problem. So now I'll Just a minute. I'll use my iPad. Okay, so one more thing is, yeah. So next is that now SVD is okay, right? So next is that now I'm coming to what I can say, what this PCA does, what this SVD application and all that, right? So first let me show something, then maybe I'll go for this theory of PCA and other things. So today I'll go in the reverse way. First I'll show you some commands and other things, because that you'll be more interested in, and then I'll show that yes, why this is happening. तो पहले तो हम कुछ ऐसा देखेंगे MATLAB पे कि this something is happening because of SVD and something is useful happening because of SVD, right? And then I'll tell you why this is happening. Okay, so let me see. Sorry, yeah. So I'll move forward. So I will load one image in MATLAB first, right? So clear, I think first I should clear all the variables. Fine. So I'll load one image in. So this is something which I said that yes, I'll be doing. Yeah. So everyone is familiar with this image. Okay, sorry. I should pick a column. Yeah. Everyone comfortable with this image command. IMG is the image, imread is the command, cameraman is a standard image in the MATLAB, and you see it's a, I mean, so but here the issue is that it is in unassigned integer unit format, so I should make it in double, I mean decimal, right? So that I'll do by this command. Yeah. So now please note that now it is in double format, right? So if you print, see earlier I printed, so it was integers 117, 12, whatever. Now if you print, you will get simply decimal numbers between 0 to 1, right? So now this is your image. So what is this image? Let me show you what is this image, what I have loaded here. Image, right? So all of you can see this image, right? Everyone, this image. Agree, right? So any idea what I want to do with this image? This is 256 cos 256 matrix. This image is size of image. I'm just printing in front of you. What happened? Sorry, something. Okay, yeah. Size of image 256 cross 256. So anyone, what do you think? What we are going to do with this image? 256 by 256 एक हमारे पास matrix है, that is nothing but image. We want to apply SVD on this image to, what we can say, to reduce the dimensionality, right? So I'll come in very great detail, but first I want to show, because I just want to convince you people that yes, SVD does help us, right? Please see that yes, SVD does help us, right? So what I want to show then, if you take the, okay, let me make it like this, right? Yeah, this is the image. So then if you take the, this is a matrix 256 by 256. Fortunately it is image, so it is a square matrix, but not an issue, right? So if we take the SVD of this image, right, SVD of this image, take this SVD, and then I'll take this USB, not D, otherwise it would be confusing. So we are doing SVD on this matrix. Agree, all of you? So if we do SVD on this matrix, we will get some U, we'll get some V, we'll get some S. So these are here. You see on the right hand side in the workspace. S is there, U is there, and V is there. Till here, everyone comfortable, right? So we have an image, we did SVD on that image, and we obtained U, S, and V. And now we want to see, I said, where is the singular values in this? In S. So we are particularly interested in S actually, right? कि वो S क्या है? पहले तो S समझना है मुझे. क्योंकि singular values are in S. U and V are having the eigenvectors. So singular values are in S. So that means that what is S actually, right? So what we can do, we can print S. S हमें देखना है actually. Yeah. So S, what we can do, we can see S by this command diagonal of S, right? So diagonal of S. What the property I told you about S? That the singular values, it will be 256 cross 256 cross 1 na matlab 256 cross square cross 1 ye hoga. So this is S, you see. This is S, diagonal of S. I hope it is visible to everyone. Is it? I'll close the figure now, right? So I'll close the figure. So then I think now it is more clear, right? So one property I mentioned about S, is that property satisfied here, everyone? What property I mentioned? Anyone? Can anyone tell what property I mentioned about S? What property I mentioned about S? Anyone? What property I mentioned about S? अरे कोई तो बोल दो. Diagonal, then diagonal will be in decreasing order, right? And you can see here, see the diagonal entries. First is the largest one, then smallest, then smallest, then smallest, then smallest, then smallest, and after, I mean, maybe 30-40 entries, it is less than 1. So what do you think? That yes, all the information of this image or matrix is only in first few entries. Maybe see iska size dekho aap, this diagonal of S, this is 256, right? Because it is a matrix of 256 cross 256. So how many diagonal elements? 256 cross 1, right? क्योंकि diagonal 256 cross 1 होंगे. But most of the information is only because पहली वाली जो ये singular values हैं वो significant हैं, बाद वाली तो सब less than 1 हो गई, फिर even less than वो हाफ भी हो गई बहुत सारी, फिर उसके बाद तो देख रहे हो आप जीरो हो गए almost. So I just want to mention that yes, this is what the singular value decomposition says, that most of the information is in the first few entries. अब ये कैसे हमें पता चलेगा कि जो मैं कह रहा हूं वो वैलिड है कि नहीं? तो मैं क्या कह रहा हूं एक्चुअली कि सब, you said that, see what we are doing dimensionality reduction. So I'll come to theory part later, क्योंकि कल मैंने theory की थी तो आप लोग बहुत बोर हो गए थे. So what I wish that I'll do the first this MATLAB part, and then I'll tell you why this theoretically, why this has happened. पहले तो MATLAB कर लेते. So whatever I'm saying, dimensionality reduction, what does it mean by that? I don't want to use it's all 256 entries. I want to use only a few entries, and I should be able to achieve this figure without any distortion or without any problem. This is what the target is. Agree, all of you? So what I defined, then I defined one more image, right? And how I defined this image, that this is, you can see what is the command here. What is the command? I'm using all rows but first column only. I'm using first column only. Please make sure I'm using first column only. S की सिर्फ first entry मैं use कर रहा हूँ. First row first column, that means first entry. And V का भी मैं first column use कर रहा हूँ सिर्फ. Agree? And then I'm just showing IMSO this image 1, and I'm just showing what you can see from here. Please do reply. Today the participation is little less. I request all of you, please do little bit messaging at least, right? I'm not saying just speak, but so what you can see, instead of 256, I just took one element. Which element? Which is the highest singular value, right? Highest singular value I took, only one, and I'm getting the figure likewise as is the original figure. Is it, I mean, am I clear to everyone, and are you convinced with my statement, or any concerns? Anyone? कि सिर्फ पहली एंट्री यूज करके ही हमने जो पुराना फिगर था हमारा वैसा ही फिगर हमें दिख रहा है. Of course it is not clear, but at least the pattern is same, only using. So will it happen if you take any S entry? No, you are taking the largest singular value, because यहाँ देखो आप command, S is the first row, first column. So you're taking the largest, and S is what? And that I told you that, yes, why this is important that it is in decreasing order, because then you can very easily choose first few big numbers. So am I clear? I mean, no response from audience. It is not good for a teacher. I mean, मुझे पता ही नहीं चल रहा कि मैं समझा भी पा रहा हूँ कि नहीं. But those who are listening, so I hope they can tell that yes, what I'm claiming is that since it is in decreasing order, so I know the first entry is the biggest one. Since I know the first entry is the biggest one, so I started taking, thank you Manisha, thank you Shandeep. So I started taking the first one, and the first one even giving me a very beautiful visual. Vishal, thank you. If we take a few entries, so suppose I'll define a function, right? See, that's why I didn't need to type. I just made it earlier also. So I made a function, suppose, right? This is the function I made, and this is the function of n. और वो n क्या है? कितनी entries आप लेना चाह रहे हो s की? Agree? So I made this function, and now if you so IMSO, and maybe what you can say, IMSO q, and maybe you can take 5 values. That means what? You're taking 5 values of s, first 5 values of s, right? And then you sort the picture. Wow, क्यों करना हमें 256? Only in 5 values we obtained that figure, जैसा कि हमारा original figure था. अगर हम 20 ले लेंगे तो क्या होगा? Distortion hai, I agree. I'm not saying it is correct, but you see, in only 20 we obtained that figure very closely. And if I take 50, even a normal eye cannot distinguish that, yes, what is this figure and what is that figure. What was the original? Can a normal eye distinguish that, yes, what is the difference between this figure and the original figure? No. I mean, it is hard. So what is the conclusion we drew from this analysis, whole analysis? Anyone? What is the conclusion? That yes, we did dimensionality reduction using this SVD instead of 256. If you take 100, even you cannot imagine. I mean, any difference between the original image and this one, right? So instead of 256, this SVD helped us to use only a few entries, and that's why this S is arranged in the decreasing order. Please try to understand, every single point is crucial. अगर ये decreasing order में ना होता तो आप नहीं कर पाते. Agree? Because then how do you know that which one is the largest number and which one is contributing most, or which one is having the most information. And that's why this S is coming in that way, that it is coming in the decreasing order. So, I mean, whatever the example I presented here, is it okay to everyone? Or anyone having any concerns? Please do let me know. Anyone? So dimensionality reduction with SVD, is that fine? Arey, koi to bol do at least. I mean, I hope. Okay, I understood. Today is the weekday actually, right? So most of you are in some work, but still, I mean, I just want to confirm that whatever I showed, it is convincing. It is, you can relate that yes, whatever the mathematics says and whatever this programming when you do, whenever you, and you people must have done this. I agree. I'm not denying. I'm not denying. You must have done this figure image wala ye sab kar rakha hoga aapne SVD se. But I'm just showing you that yes, how, I mean, how mathematics has helped us from eigenvalue to SVD and from SVD to this point. This point we have not reached yet. I'll now in the next half of the session I'll discuss why this has happened. ये क्यों ऐसा जादू थोड़ी हो गया? I mean, this is not really a magic. I mean, not at all actually, right? This is not really a magic. It has certain reasons, as I showed you yesterday, that a singular value is not a magic, right? It started from eigenvalue, people developed the theory, and then they obtained, yes, this is useful. So I'll explain you in great detail that what is the logic behind this this why what this is happening here, right? कि 20 लेने पे कितना हो गया, 40 लेने पे कितना हो गया, actually ये करता क्या है, ठीक है? So I hope this is done, right? So now I am moving to the application of this SVD in principal component analysis. So next is SVD in principal component analysis, right? So let me okay, I'm winding up this MATLAB. Just a minute. Okay, so how I can stop my sharing? Stop sharing. Okay. Yeah. Okay. So then, just a minute, because I need to now switch on my. I mean, switch to my iPad to write it. Okay. So this is where. Okay, so now I want this sharing rights on this, so I'll call to. Am I audible? Anyone please confirm? Am I clearly audible? Anyone? Yeah, I think so, right? And I think, yeah, thank you, Prem Kumar. So, and I think, yeah, so I need the sharing rights on this iPad. So just wait for a minute. I believe that you can see. Yeah, you can see my screen, and I'm audible clearly. Any concerns regarding audio video? Please do let me know. Anyone? Fine, right, audible. The screen is visible. Some noise is there. Okay. Now is it there? Any noise now? I mean, now it is perfectly audible, is it? Yes, fine. Thank you, thank you. So now it is perfectly audible. Okay, my screen is visible, so that's fine. So now I'll be discussing the magic you have always seen in Python and MATLAB, whatever, right? So why this is happening in, I mean, in this SVD? ये एकदम से 50 elements में ही हमें ऐसा क्यों मिल गया? So actually, my topic today is that SVD for PCA. This is interesting. Nah? This you people are expertise in this topic. I don't know much. I admit first, right? I mean, I know SVD. I know SVD in PCA, but more as someone asked yesterday that what are the feature extraction techniques or dimensionality reduction techniques. So you people are, I do believe that you people are expert in that, right? So, but before that, I just want to, uh, yeah. So I just want to. So again, I'll start from the title only, right? So now you people, I hope you people will support me. I mean, in messaging, SVD we have done. So this is done. This is we are happy that it is done. What about principal component analysis? Can anyone unmute himself and herself or herself and say something? What does it mean by principal component analysis? I mean, करना क्या चाहते हैं हम? क्या करते हैं principal component analysis में? What we exactly do in principal component analysis? Very scratch. I'm not going in detail. I mean, what technical nahi? Feature reduction, good. Feature extraction, maybe we can say that. Dimensionality reduction, so or feature extraction. Okay, so what exactly we do, I'll come little late, but first I'll just try to mention a few. See, as I said that I'm mentioning from mathematics point of view, basically from SVD point of view. So what PCA does, so what we had actually, we had an image that was a facial image, right? So we had an image that was what, 256 cross 256 matrix. Agree? अभी हमने सबने देखा. It was 256 cross 256. So if you convert it into vector, what it will be? 2 to the power 8 into 8, 8 plus 8 basically, 16 cross 1. So don't you think it's a large enough? I mean, it's a large vector to deal with, right? So what is the conclusion? That yes, dimensionality is very high. I mean, not very extremely high, I can say, right? And it is even for a small picture, a small image, not a very large data or something, right? Very small image, and the dimensionality is like this, is very high. So what we can do two things. So then it leads to the problem in difficulty in difficulty in difficulty in analyzing it, right? So let me write it in a clear way that difficulty in analyzing. So please do understand, I'll just try to mention again that yes, we have an image, we have very high dimensionality. So two things we can do, right, very immediately. One is that dimensionality reduction. Two things basically the same, right? Dimensionality reduction or we can say that this is extracting relevant features, right? Extracting relevant features, which is nothing but feature extraction, right? Which is nothing but feature extraction. So the problem we understood is that yes, we are facing high dimensionality data that is not at all be used as it is for our practical application. It is very difficult to use that for our practical applications, right? Then we want to do something with this data, right? We want to uh, small, make it small. We want to make it, I mean, just like we did in MATLAB. You see what we did, that yes, what we did, uh, yes, we took the only largest 50 singular values and we are happy. I mean, we don't need the other garbage. We just took the 50 values, largest 50 singular values, and we are happy. So this something this kind we want to do. So what is principal component analysis? As I said that I'll start always from the title, right? Title एक बार clear हो गया तो समझ में भी आएगा कि करना क्या है. So next is that suppose you have this data, right? You have this data. So what do you think? So principal component. Okay. So what is the principal component basically? Anyone? So here, okay, I just want to listen from you people at least. You are, I mean, expert of these, and most of you, this principal component analysis and other things. So anyone? What does it mean by principal components? What is it? Dimensionality reduction is okay, but I mean, what does it mean by principal component? So principal क्यों कहे जाते हैं या principal component क्यों कहते हैं उनको? Analysis is okay, principal component analysis is okay, but there should be something which is principal component, right? There should be something which is principal component. So what does it mean by principal component? Anyone? Dr. Manisha, thank you, but I just want to have even more precise way of explaining it, that what do you mean by principal component? Actually, new values or dimensions, new values of data, I believe, right? Vishal Gupta, new values of data, right? Data की जो पुरानी values थी उनसे ही हमें नई values मिले, उन्हीं को फिर हम एनालिसिस, वो ऐसा ही है. New values are dimensions. So there is some I think confusion. Is it, Vishal? What new values? I mean, किस चीज की new values? Yes, right. So what principal component? Achha, okay. Now just let me know. Eigenvectors are dependent features, important features. Yeah. Okay. Can anyone tell me what principal component analysis gives you actually? What principal component analysis gives you? What principal component analysis gives you? Okay, so I'll spend a few minutes on this. Maybe then we can move forward. So see, in this way, this data we can think as in a spread in two direction. One is in this direction, and one is we can think of this direction. Right? We can take this is spread in. So which has the, this is having the most spread, right? इधर ज्यादा है, most spread along this direction.
देखो, what I'm going to cover, what actually principal component analysis gives you, and why, then how SVD is useful in it, why other concepts are not useful in it. But first we have to understand that what actually principal component analysis gives us. Principal component analysis hai kya? What does it mean by principal component, right? So that I'll do little bit, and then I'll come that how this SVD helps us. So please tell me whenever you don't feel comfortable. So maximum spread of data along this direction, right? That means what? It is having large variance, right? And this is having a small spread, right? Comparatively smaller spread. So that means small variance. So what is the, no, I'll not write principal component. What is the key idea? I mean, करना क्या चाहते हैं principal component analysis से? See, there are two questions. First is what we want to do with principal component analysis, and then how SVD helps us. See, if you know what we want to do from principal components, then maybe there might be some other topic also which can help us other than SVD. But first we should be very clear actually what we want to do with this principal component analysis, right? So principal component analysis, the key idea is what is the key idea? I can write data can be projected along this direction, while capturing the important information. And these direction, ये जो word है ना, data can be projected in this direction while capturing the important information, right? And how, the question is how do you determine these directions, the directions with largest variance? And the answer is that I was expecting from you people. As I said, I admit it. I mean, it's not any harm to admit it that you people know these things in advance. But I'm just telling if you don't know, in case any of the audience. So the key idea is that you have a data, you have a spread of data in some certain direction, right? So the most spread in one direction, that means the most variance, the large variance in that direction. So that direction will be useful for us, right? That direction will be useful for us. That means our key idea is that data should be projected in this direction. But the problem is, how will you find that direction? So the answer to this question is, so the answer is these directions are called principal directions. See, I'll spend a few minutes on title. I always spend, because if you don't understand the title clearly, how do you work on it, right? So that's my belief. So the idea is that these directions are called principal directions, along which, okay, so these directions are called principal directions, and using PCA we do it. But you get the principal direction. What is the use? Okay, till here it is fine. Anyone? See, your participation is, no, screen is visible. I can see Vishal. Maybe it's some problem with your end, but because I logged in from two devices, but your participation is little less from your side. I'm sorry, but please be little bit, because क्या बोलूं मैं, आप लोग सब हमसे सीनियर हैं. If you participate, then I'll also be encouraged to, I mean, na. So, and this is, if you know these things, you can tell me. I can immediately go to the some other thing. That's very fine. All of you know these things. Should I move forward? Anyone? Vishal, did you get the screen? I mean, are you able to see the screen? No. Others? Are you able to see the screen? Others? Yes, I think because I can see. Dr. Manisha, Abhishek, yeah. So Vishal, maybe you can disconnect and then connect. I don't know. Yeah, thank you. So I just request to all of you, please do little bit. So is that, I mean, all these things you know, you people know, so that I can move forward, or you don't know, and it is not seems interesting, so that I can change at least the way which I'm going. Don't know. Okay. Others? So I'm just trying to mention you that yes, see, before going to the advanced thing, first we should know that SVD is fine, right? PCA, at least we should know that what we are doing in PCA. Khali, the command likhna is not a PCA, right? And that you all believe, that I also believe. So PCA is actually, I told that yes, you have a data, you have a large variance in one direction. Then the key idea is that your data should be projected in that direction, because while keeping, क्योंकि अगर एक डायरेक्शन का डेटा हमें मिल गया, सारा डेटा एक ही डायरेक्शन में, so that direction can be useful as for us, right? Just like we saw in SVD. तो ये तो हेल्पफुल हो जाएगा अगर एक ही डायरेक्शन में सारा डेटा मिल गया. So the key idea is this, and how do you determine these directions? Okay, you people don't know, then tell me where I mean, not good. I mean, where this class is not going good. I think we are doing it in a very nice way. So I request your support little bit, right? If you wish. So how do you determine these directions? That with the largest variance, the idea is this principal component analysis. But here it is principal component, not principal directions. So some of you said that principal component is the new value, right? So how did you get that new value? Anyone? So the idea is we project the data along projection. All of you heard of it, at least projection. सुना तो होगा at least. नहीं याद है, it's okay, but projection. How many of you have heard of it at least? Anyone? Yes, right. So सुना है, ठीक है, good, thank you. So we project the data along these directions, these principal directions, to get the so finally we landed up to the word principal component. Yes, so now this is what actually the meaning of principal component analysis, that yes, we have a data, first we find the principal direction. After finding the principal direction, PCA gives you the principal direction, please make sure, right? So PCA gives you the principal direction. After getting the principal direction, you just project the data along these principal directions to get the principal components. और वो principal components जो हमें मिलेंगे, that will be useful for our analysis. So till here, everyone, at least you know, you understood the what actually this means by principal component. ये तो at least समझ में आ रहा है, फिर आगे देखेंगे जो भी है. And where does this SVD is involved in this, that will look, but at least till here principal component क्या है, and that principal component basically that the components which have the maximum. What do you understand? I mean, what do you think this principal component means? Anyone? What do you think this principal component means? The components which have the maximum information, right? Isn't it? right? So how do you get this principal component? First we get the principal directions, and after principal direction we take a projection, right? And projection kaise lete hain, that we will discuss, right? So we take a projection of the data along these directions. ये आपको सबको पता है, you know that. I mean projection all of you know, right? कोई एक direction है, उस पे कोई point है, तो उसका projection अगर लेना है तो कैसे लेते हैं? That you know, I believe so. If you don't know, you can have a look, not an issue, right? So please have a look at the projection topic. I'm not going in to discuss that detail, but after finding these principal directions, we take the projection of data to get the principal components. तो ये तो बात हुई कि करना क्या है हमें, right? What does it mean by principal component analysis? What it means that yes, first we have data, second, so the aim actually, what we have data, right? We have data, we have to find principal directions, and then find principal components. And next is this, we have, this is the first, this is the second, and what SVD does. SVD कैसे help करता है हमें यहाँ, right? These are the three questions we still have, and we have almost half an hour, more than half an hour. I'll try to complete this whole thing, that actually how to find these principal directions, how to find these principal components, and what actually SVD does in this to get the principal components. Those are useful for us. Any queries till here? Anyone? I mean, is it going okay or nahi bolna hai? It's okay, fine, but just let me know that it is going okay. I mean, it is not boring, it is not torturing, it is not like not interesting or whatever, right? So just let me know that. If you feel so, I can change, as I said, right? So the first question is find principal directions. So principal directions, right? So the idea is what I'm going to do now, I'll give you a brief, not very detailed, right? I'll give you the brief idea of this principal component analysis, the PCA, right? So thank you all. So the idea is that you have a data, right? So given the data, we have the data, suppose x1 tilde, x2 tilde, and so on, xn tilde. So n is what? This is basically number of repetition of an experiment. What does it mean? कि कोई experiment है, आप n बार कर रहे हो, agree? You're doing that experiment n times. That's fine, completely fine. And this is the data set you have, and each xi is basically, it is m cross 1, which is where m is basically what? Where m is number of features. Yeah, please, I just want to mention here that I'll share this file, this PDF file. So I got one request yesterday, so I'll share this file with Tiwari sir in PDF form. So m is the number of features. So x1 is basically m cross 1 vector, right? And you're doing this experiment n times. So all of you are very comfortable with this, that we will be having this data. And so if you write it in a matrix form, suppose x tilde अगर matrix form में लिखना चाहते हो आप, यहाँ पे कैसे लिखना है आपको? Column wise. So x1 is the first column, x1 tilde, x2 tilde is the second column, and so on, xn tilde is the last column. So what will be the size of x tilde? Anyone from the audience? What will be the size of x tilde? Anyone from the audience? Yeah, please. कोई तो बोल दो. You are writing it in column wise, because these are small things. I don't know, maybe I should ask or not, but it's okay. So no one wants to say. Okay, m by n, right? So m is the number of rows and n is the number of columns. So this is the matrix you get given data. Okay. So then what is the PCA procedure? So estimating mean. So first of all, you estimate the mean, right? How? What is the formula for mean? 1 over n summation of I equals to 1 to n xi tilde. Everyone comfortable till here? Everyone, please, yes or no? Just yes or no. I mean, you have a data, you are just estimating the mean, right? This is all. And we are particular. Thank you. Someone replied. Yeah, thank you. So see, the direction was with the largest variance. So we have why we estimated mean, because we want to go to the variance, right? To give direction was along with the variances maximum, largest variance, right? So हमें वेरिएंस तक जाना है, so we will start from mean, क्योंकि डायरेक्ट वेरिएंस नहीं जा सकते आप. We have to find mean and then we have to subtract it, right? So define xi bar, not tilde, please make it clear, right? Xi bar is xi tilde minus mu bar. और अब आप लोगों को पता है कि वेरिएंस कैसे डिफाइन करना है, राइट? सो covariance be denoted by r of suffix x, so that is nothing but 1 over n minus 1 summation of I equals to 1 to n xi bar into xi bar transpose. Everyone knows that, right? xi minus mu का होल स्क्वायर होता है, तो xi बार को xi बार से ट्रांसपोज से मल्टीप्लाई करोगे, so you will get xi minus mu का होल स्क्वायर, and that is nothing but your variance. So everyone comfortable with this equation? Please do let me know. Comfortable with this equation? क्योंकि वेरिएंस की डेफिनेशन क्या होती है? xi minus mu का होल स्क्वायर, राइट? सो इफ यू multiply xi by its transpose, you'll get this, right? So all of you, I hope so. Manpreet, thank you. Manisha. So if we take x bar as a matrix, please make it clear, right? And now we are putting it as a row. पहली रो में हमने रखा है x1 बार ट्रांसपोज. देखो ठीक है, x1 बार यहां से है I equals to 1 to n. तो x1 बार तो यहां से था, तो ट्रांसपोज, क्योंकि ये सारे कॉलम वेक्टर्स हैं, तो अभी रो में चेंज करना है तो ट्रांसपोज करना पड़ेगा. एग्री? फिर x2 बार ट्रांसपोज को यहां रखा हमने, ऐसे करके हमने xn बार ट्रांसपोज को यहां रखा हमने, और ये एक मैट्रिक्स बना लिया x बार, ये एक मैट्रिक्स बना लिया. सो यानी कि ये rx फिर क्या हो जाएगा? Is it okay to everyone? Yes, we had data, we found its mean, we found its covariance, and then we wrote this. This is the covariance, right? Rx, and this is the form we obtained. आप लोग देख सकते हो, इस easy one, right? कोई बहुत इसमें difficult नहीं है, because क्योंकि हमने रो वाइज कर दिया है, तो ये ट्रांसपोज पहले आ जाएगा और x बाद में आएगा, ठीक? और we can write it as, and please make sure that अब ये x बार की डायमेंशन क्या हो गई? Let me write it in red, not m by n. This is now n by m, क्योंकि आपने उसको ट्रांसपोज कर दिया. प्लीज राइट एवरीवन, 100% क्लियर. So then again I'm writing this can be written as x transpose x, right, where x equals to 1 by root n minus 1 times x bar. So is it clear to everyone till here? Rx equals to x transpose x. और हम यहाँ क्यों आए हैं, ये भी आप लोगों को समझ आ जाना चाहिए अब ये इक्वेशन देखने के बाद. दिस इक्वेशन maybe I'll call it 9, क्योंकि पीछे वाली इक्वेशन भी हो सकती है कुछ, ठीक है? Any one of you got this idea why I found Rx in this form? First of all, is it clear to everyone that we obtained Rx, that means covariance, in this form? Whatever the calculation I did, first I just want to make it clear. And please make sure that what we are going to do, we are going to find this principal directions. हमें एक बार principal directions मिल गई अगर, then we can find the principal components also. But before that, we have to find principal directions, and there we use this SVD. यही तो है ना, application of SVD in PCA. That's what we are learning, right? So how this SVD is useful. So everyone, please do let me know. At least yes no बोल दो भाई, मुझे समझ में आ रहा है कि हाँ ठीक है, whatever the calculation I did using this data. See, these are small calculations. No big, simple mean है, simple variance है. Then you have to just take the transpose of matrices. Thank you so much. I mean, you all replied. So अगर किसी को नहीं आया, then we can repeat. It's not an issue. So x is this, x bar by n root n minus 1. So अब ये finally आपको x transpose. Okay, now can anyone give this favor to me? Why we obtained this rx in this form? इस फॉर्म में rx को क्यों लाए हम? किसी को कोई गेस आ रहा है? Whatever we have learned from past 2 lecture, past 3-4 hours, why we wrote rx in this form? Anyone? नहीं. Why did we write rx in this form? Okay. Eigenvectors. Yeah, actually, I don't know what you want to convey, but you could have written even in a sentence, but it's okay. Thank you for your answer. Actually, if you see, what was the eigenvalue decomposition, this singular value decomposition, U S V transpose. What was the V, U or V? V क्या था? V क्या था? Eigenvector of A transpose A. राइट. एक्चुअली और एक चीज और भी ध्यान रखो आप, जो ओरिजिनल डेटा मैट्रिक्स है वो है आपका एक्स टिल्डा, राइट. एक्स टिल्डा से आपने एक्स बार बनाया, राइट, एंड एक्स बार से आपने एक्स बनाया. सो बेसिकली दिस एक्स हैज दैट ओरिजिनल इंफॉर्मेशन, राइट, नॉट एन इशू, है ना. एक्स की जो है वो एक्स में ओरिजिनल इंफॉर्मेशन है, मे बी इट इज ऑब्टेन्ड बाय सम मॉडिफिकेशन, राइट. द ओरिजिनल इंफॉर्मेशन वाज इन एक्स टिल्डा, देन यू ऑब्टेन द एक्स बार यहां से आ जाएगा, ठीक है, ये डिफाइन किया आपने. दिस इज नथिंग बट द वेरिएंस सब्ट्रैक्टेड इन द डेटा, एंड देन यू obtain x. So try to understand that. Yes, how should I write it? Just a minute. Let me use this color, and then now perform the eigenvalue decomposition of Rx. क्योंकि आपको पता है x ट्रांसपोज x will be again स्क्वायर मैट्रिक्स, राइट. सो आइगन वैल्यू डिकम्पोजिशन आप निकाल सकते हो इसका. आइगन वैल्यू डिकम्पोजिशन बेसिकली मींस यू कैन फाइंड इट्स आइगन वैल्यू एंड यू कैन फाइंड इट्स आइगन वेक्टर्स, राइट. दिस इज व्हाट. सो व्हाट विल हैपन? सो सपोज यू गेट, consider that v1 bar, v2 bar, and so on, vp bar are the eigenvectors of x transpose x corresponding to the p largest eigenvalue. Please make it clear. P largest eigenvalues. What does it mean? Ki p is in our hand, right? Suppose we are interested in 50. So this 50 is p. 50 largest eigenvalues, 50 largest singular values. So हम कितनी चाहते हैं ये हमारे हाथ में है. कितने से हमें लगता है कि हमारा काम चल जाएगा, कितने प्रिंसिपल कंपोनेंट्स हमें चाहिए. Got it? How many principal components we need? So this p is, let me write it clearly, that this p is number of principal components, right. Basically not number of principal component, I should not write, size of principal component, size of principal component, I should write this. तो वो p कितने चाहिए हमें? सपोज वी हैव डिसाइडेड दैट 50, so we calculated the eigen values of Rx, right? However, how long it is, I don't know. I mean, it is might be 1 lakh by 1 lakh, but we decided that p is 100. So I'll take the p 100 eigenvalues, right? 100 largest eigenvalues, and the eigenvectors corresponding to that 100 largest eigenvalues. And you all know that eigenvectors of x transpose x is what? We know that eigenvectors of x transpose x, जो कि कौन सा है ये? v1 v2 vp, ये क्या है? Eigenvectors are x transpose x. What it is? Are what? In singular value decomposition. See, now this is the point where singular value decomposition helps us. Eigenvectors of x transpose x is right singular vector of x. Right singular vector basically means कि x को अगर हम ऐसे लिख रहे हैं u सिग्मा v ट्रांसपोज, तो ये वाला जो v है इसको हम राइट सिंगुलर वेक्टर बोलते हैं. राइट. सो टेक्निकली हमें काम किस पे करना चाहिए था? आइगन वैल्यू डिकम्पोजिशन ऑफ Rx, राइट? वहां से हमें ये v1 v2 v2 मिलते हैं. नहीं, हम सीधा देयरफॉर, प्लीज थोड़ा सा देखो, थोड़ा सा टफ हो सकता है फॉर सम ऑफ यू माइट बी वेरी कंफर्टेबल विद दिस, आई डोंट नो. देयरफॉर इंस्टेड ऑफ considering x transpose x, now we consider x only, and eigenvalue decomposition. x transpose x का क्या? हमें eigenvalue decomposition चाहिए था. हमें अभी क्या चाहिए? x का सिर्फ singular value decomposition, right? So now we consider instead of considering eigenvalue decomposition of x transpose x, considers svd of x only. क्यों? क्योंकि जो आइगन वैल्यू डिकम्पोजिशन से आपको मिलता है x ट्रांसपोज x की, वो आपको डायरेक्टली x की svd से मिल रहा है, right? Because what you do just svd of x, right? What you get? svd of x, and we get, क्या करना है आपको? x equals to u sigma v transpose. You get that, right? So here you know that this v is the right singular matrix of vector of matrix x, and ये v क्या है? एक्चुअली v के जो एलिमेंट्स होंगे वो क्या होंगे? पहला कॉलम होगा उसका v1, दूसरा कॉलम होगा v2, राइट? तीसरा कॉलम होगा v3 एंड सो ऑन, फिर एक कॉलम होगा vp, राइट? मे बी आई शुड या, राइट? एंड देन एक होगा vp प्लस 1 एंड सो ऑन. कितने होंगे? as many size of v, right? We are interested in, ये जो पहले वाले होंगे ये क्या हैं? These are the p right singular vectors, right, corresponding to p largest eigenvalues. अब आप लोग याद करो हमने क्या किया था? We took first element of S, then first vector of U and first vector of V, right? We took two elements of S, then first two vector of U, first two vector of V. We took P elements of S, those P which are largest, right? Those P which are largest. P elements of S, P elements of U and P elements of V. तो ये देख रहे हो आप कि how SVD helps us, that yes, we have a data, from that data we define this x transpose x, और उस x transpose x पे हमें एनालिसिस करने से अच्छा है कि हम सीधा, ठीक है, क्योंकि अगर आइगन वैल्यू डिकम्पोजिशन करेंगे तो क्या प्रॉब्लम आएगी, वही इनवर्स की। हाउ डू यू नो दैट यू इज इन्वर्टिबल? तो उसका आइगन वैल्यू डिकम्पोजिशन करना फिजिबल नहीं है एक्स ट्रांसपोज एक्स का। इससे अच्छा है कि हम एक्स का सिंगुलर वैल्यू डिकम्पोजिशन कर लें। क्यों? बिकॉज वी हैव सीन दैट आइगन वेक्टर्स ऑफ एक्स ट्रांसपोज एक्स इज नथिंग बट राइट सिंगुलर वेक्टर ऑफ एक्स। इस चीज को आप लोग अगर समझेंगे ना, I am 100% sure when I read it first time, I was like amazed, right? So when you, if you, by the cool mind, if you understand this concept that yes, instead of doing that eigenvalue decomposition of x transpose x, that is one way. No one is doubting on it. But there are concerns. We discussed it already in the yesterday's lecture. Today, I showed that instead of discussing the eigenvalue decomposition of x transpose x, we can do the singular value decomposition of x only, and we get the same v1, v2, vp. And these v1, v2, vp are called eigenvalues sigma 1, जो कि सबसे बड़ी है, राइट? आई टोल्ड यू लाइक ऐसे ऐसे अरेंज्ड है ना, यही तो बताया मैंने कि जो पहली आइगन वैल्यू है उसकी सिंगुलर आइगन वैल्यू या सिंगुलर, अगर आइगन वैल्यू बड़ी है तो सिंगुलर वैल्यू भी बड़ी होगी, रूट ही है उसका, ठीक है? सो दैट आर अरेंज्ड इन दिस वे, एंड these are called the Pca vector, right? The Pca vector, we said that the principal axis or principal directions. So principal axes are nothing but these. What? v1, v2, vp. तो ये आपको प्रिंसिपल डायरेक्शंस मिल गई। और प्रिंसिपल डायरेक्शन ही लिखता हूं मैं, क्यों एक्सेस लिखूं, कंफ्यूजन हो सकता है। सो दिस इज हाउ यू गॉट दिस प्रिंसिपल डायरेक्शंस। So at least 50%, 60% clear what I explained. मेरा explain करने का logic ये था in this discussion that you have a data, we have arranged it in terms of x transpose x. We could have done the eigenvalue decomposition of this x transpose x, but we have seen that it may not be possible, right? Instead, we saw that yes, it is not, and this is a square matrix. X transpose x is always a square matrix, so you can do the you can find the eigenvalues, that's for sure, not an issue. Only problem was with that inverse, right? So instead of doing the eigenvalue decomposition, we do the singular value decomposition of x, because there is no problem in this singular value decomposition, and we get the same v1, v2, vp, which is the right singular vector of x corresponding to the largest eigenvalues, right? And these vectors are the principal directions which we were looking after. तो SVD help, तो दो क्वेश्चन के आंसर्स हमने कर लिए यहाँ पे। इफ यू सी, प्रिंसिपल डायरेक्शन हो गया और SVD हो गया। What is remaining left? Anyone? What is left? What is left? प्रिंसिपल कंपोनेंट। एसवीडी का यूज आ गया, प्रिंसिपल एसवीडी, दिस वी डिड ना अभिषेक here we use na svd of x, then only we got this v1, v2, vp na. Instead of doing eigenvalue decomposition, we are doing svd, singular value decomposition of x. That's how we are getting this v1, v2, vp. And I showed in the MATLAB that how do we do this svd of x. Abhishek, is it fine? Abhishek Tripathi, is it fine? Others, anyone who, I mean, who found it useful and who found it interesting, he can ask if he have any he or she have any queries, right? So the only thing left is principal component. अभी तक नहीं मिला, टाइटल ही नहीं हमें समझ आया कि principal component analysis करता क्या है, होता क्या है principal component. So the idea is we are still left with what is principal component. Principal directions तो मिल गए, so that means what, v1, v2, vp, the eigenvectors of x ट्रांसपोज x, या देखो v क्या है, जो सिंगुलर वैल्यू डिकम्पोजिशन में v क्या है, दैट इज आइगन वेक्टर्स ऑफ x ट्रांसपोज x corresponding to largest eigen values will give you the principal direction. तो अगर आइगन वैल्यू लार्जेस्ट है, इसका मतलब डेटा की इंफॉर्मेशन उधर ज्यादा है, मतलब उसको हमें रिटेन करना है, मतलब those directions are principal directions. Is it okay to everyone? Right? So fine. So still left question is principal components, right? Principal direction तो ठीक है, principal components अभी भी बचा हुआ है. I wrote some line. Can anyone recall how do you get the principal component? See, अगर ये पता चले ना, principal component analysis is what? Getting these principal components and then go for further analysis, whatever you people do. As I said, I'm not the expert. So, but principal component actually क्या है? I wrote one line. The principal components are given by the projection of the data vectors along these principal directions or axes. So is it convincible? Is it okay to everyone that yes, principal directions we have already obtained? Now it is time to compute principal components, and that is nothing but the projection of xi bar. So technically what it is, projection of xi bar, right, along principal axis, right? Is that fine? So principal of xi bars along this principal axis, how will we do that? Anyone? Can anyone recall what is the procedure for this projection? Can anyone recall what is the procedure for this projection? किसी को याद है? मतलब it's okay. I mean, if it is not, then still. But if you remember, then we can. Anyone? नहीं, अच्छा ठीक है, चलो. So projection is basically nothing but you take the inner product. So how do you take the inner product? You have ये जो आपके ये V1 V2 VP है, इनका साइज क्या होगा? क्या लगता है आपको, क्या होगा? These are all m cross 1, right? क्योंकि m by 1, जब आपको आपका जो x मैट्रिक्स है उसमें क्या m cross 1 ही तो है, तो m cross 1 वेक्टर्स हैं ये. गुड, राइट, someone wrote that. Thank you. So thank you, Abhishek. So if you put these V1 V2 in row way, of course you have to take them transpose, right? क्योंकि आपने you have to take in, see, mathematics is always written in a clear way. ऐसा नहीं है कि कुछ भी, क्योंकि V1 you have taken column vectors, right? So V1 transpose would be row vector. That's why we are taking as a V1 transpose. That's it. Just a notation, right? It's not like transpose क्यों किया क्या किया. This is just a notation. Reason is that V1 V2 VP they are taken as a always column vector, right? ऐसे तो उनको रो बनाने के लिए we took the transpose and you just made. So what will be the size of this matrix? Agree, everyone? Right? And you have to take the inner product. So that means dot product with data, right? So that you know. And this xi is what? What is the size of each xi? हर एक xi, एक xi क्या था आपका? m cross 1 था. हर एक xi क्या था आपका? m cross 1 था. Agree, everyone? So finally you will get a new vector xi which is again will be of p cross 1. ध्यान दो क्या मैंने बोला था, p is the size of principal component. आपको एक नया p क्रॉस 1 मिल गया, हमारे पास था m क्रॉस 1 बड़ा सा, अभी मुझे मिला p क्रॉस 1 स्मॉलर, maybe I could call it xi hat, क्योंकि जब आप इन दोनों को मल्टीप्लाई करोगे तो क्या मिलेगा, p क्रॉस 1, and this is what the principal component of xi bar. So technically और जो आपका xi hat है वो क्या है, v ट्रांसपोज xi bar. अगर मैथमेटिकली लिखें, अगर नहीं लिखना है इट्स ओके फाइन. So this is what the principal component you obtained. I told that it would be of size p. Reason is p is in our hand, how many p's we want, right? How many largest eigenvalues we want to take, which we think that it is sufficient. Just like in the image example, I took 50. I took 1, 2, 3, right? I took 50, and then you saw that in 50 it was fantastically captured that image, right? So this is what the principal component we obtained, right? So I'll very quickly, this I do in every class, so I'll very quickly do what we learned in this 2 days sessions, right? This is the end of the session, we are coming to end. I'll very quickly discuss, and those topics you can, if you feel any doubt in that, you can contact me, not an issue, right? So first we started with the eigenvalues actually, right? Eigenvalues, then eigenvalues and eigenvectors. Then I discussed what is actually singular value, first of all, right? What is singular values? Then eigenvalue decomposition and singular value decomposition, right? Eigenvalue decomposition of a matrix, its limitations and other things. Then of course we discussed singular value decomposition, right? Then we discussed its mathematics behind it, right? Proof and other things, right? Proof, discussion on this singular value decomposition, right? What we did then, MATLAB hands-on. I did a few, I mean only a few hands-on. Reason was that I knew if I could have done more MATLAB, then I would not have finished this. But this I wanted to show you that yes, this is what happens of in principal component analysis. I don't know whether you are aware of this or not, I'm not sure about it, but yes, I just wanted to show you that this is what the principal component means and how do you get it mathematically, how do you get from your data, from your eigenvalue, from your eigenvectors. So MATLAB hands-on we did, and then we did what is that PCA, right? What PCA means actually, right? Then we did that this mathematics of PCA, right? How to get this principal component from your SVD. Last we can say that SVD in PCA, right? So we try to cover this all this concept in last 2 lectures. I thank you. If you wish to have to ask any question, I welcome you. But if you don't, then it is also fine. Please, I'll share this PDF to all of you. I mean, you can have a look at it. And Tiwari sir, I think I'm done. So we can go to the audience. They can ask if there is.
So thank you. I request all the participants, please
ये बोर हो गए सभी के
pay
सभी.
attention. So any of the question, please you have, please write down. It's always be difficult, especially for the participants, to continuously pay equal attention to all the sessions, all the days.
Of course, it is difficult. I tried to make it a little bit interesting, but I think I could not. So it happens.
No, sir, it was really fantastic, and it totally fit with the theme of the FDP, like a feature engineering, feature extractions, and the SVD is the core. Some
Component
question
size
is
is
there, sir.
standard during research. Dr. Manisha, I did not get your. Can you please little bit explain what do you mean by component size is standard during research? No, I mean that is your like in image. If I get your question correctly, then I'm explaining. Please do correct me if you feel. Suppose that image extraction, right? We took 50. So suppose in 50 you feel that no, image is not that good. So you can increase it to 60 or 70. And if you feel that no, I'm okay with the 20 only, 20 largest singular value. So you just make p value is the 20 only. Is this what you are asking? I mean, I that 50 components you received. No, we just thought of like that, okay, in 50 it is okay, right? You can see the original was 256, and you see this matrix multiplication, how you are getting that 50, that is very much clear from here, right? So the idea is instead of 256, in how much you are comfortable. If you are you wish to compute your all the things on 50, then you can compute it using 50. If you have that much machinery to compute it on 100, you can go for 100. Or you are okay with the accuracy with the 20 only, then you can go with the 20 only. I think this is what you asked.
I think she is asking how many component we supposed to select for the further processing. I think she is asking.
Okay, so how many is difficult answer, I think, sir. I mean, this is up to you, right? This is up to the problem.
And
There
no
is,
issue.
I don't think there is any standard way to select how many, right? So
In the
how many is,
machine learning, if they try to extend, there is some concept like total variance explained by the component that you can consider.
yeah,
So with the limited time, we can't cover all those things, Dr. Manisha.
mathematically we have to
So please
compare
go
variance
through.
in that case. She has
Yeah,
also
yeah.
replied that mathematically we have to compare variance in that case.
Yeah. So no doubt the further exploration and studies required. So please, the fundamental things that is aimed to cover, we have covered over here. And please go on the further study from the books and blogs. You will find how to select it, what are the various procedures, and many things are there.
That
So
I
please go.
admitted in the starting of the session
Yeah.
also, that your people are this expert of this subject. I'm not, but yeah, whatever I told, that is
And that is more important. A mathematical background is more important.
so,
So no issue. I think time is also over. It is a total lunch time.
yeah.
So thank you, Dr. Kuldeep. You have taken the two session that was the most fruitful session, I think, so in this FDP, and all the participants have enjoyed it. And the recording and everything, the notes you are using,
Yeah.
Dr. Kuldeep, please share with me. I will share to all the
Sure,
participants. No issue.
sure.
And the recording will be available after the FDP within a couple of days. I take from my side, I'll share it. So thank you. We are going to end this session and we'll join again at the 3 p.m. Thank you.
Thank you.